A very good afternoon to all of you. So now myself Sanjukta Abhay Kumar, and I'll be going to take your class on this one, third topic. You all may be aware that there are total 5 topics in advanced material chemistry course, of which all other 4 are already completed, and now I am going to take this third one. Chemical, measure, trace and ultra trace analysis. Now in this course, these are the various things I am going to cover. You all may be aware of that. So now this lecture contains total 6 lectures of 1.5 hours each. And now in this lecture, this will be covered. This is the first one. So let us start with terminology and vocabulary. The content of first lecture is the terminology and vocabulary of analytical chemistry, basic overview of analytical concepts, solutions and their concentration and stoichiometry, sample resolution techniques, gravimetric method of analysis, volumetric and titrimetric analysis, and then redox titration and potentiometry. So let us go through it one by one. So the terminology and vocabulary of analytical chemistry. So let us first see what is analytical chemistry. So the definition and scope, if you see, then analytical chemistry is the branch of chemistry focused on the qualitative and quantitative determination of chemical components in materials. It bridges science and application essential in fields like pharmaceuticals, environmental monitoring, and material science. If you look into any science or any chemical branch, you find it is associated with some or the other measurements. And these measurements, everything comes under analytical chemistry. And depending on the measurement or the results obtained, now the future steps are decided, and therefore analytical chemistry is the basic branch for all the chemistry. So now where we should know the terminologies and vocabulary of analytical chemistry, why it is required. It is required because whenever you read any analytical chemistry book or any journal of analytical chemistry, you will discover the use of various terminologies. In order to understand analytical chemistry, you need to familiarize and understand its various terminology and vocabulary. So, the consistent use of terminology ensures clear communication of procedures and results. It reduces misinterpretation of data and methods in scientific discussions, and also it builds a strong foundation for advanced analytical methods. So where standardized vocabulary is needed. The standardized vocabulary ensures consistency across laboratories. It should not happen that in your laboratory you are talking something and the same thing will be differently assigned in another laboratory. So it should be, because analytical chemistry, it should be worldwide similar vocabulary, similar terminologies, and therefore the standardized vocabulary ensures consistency across laboratories, industries, and academic institutions globally. It aligns with international guidelines like ISO or IUPAC for standardized reporting, and also it is essential for reproducibility of experiments and validation of methods. So now let us see the various key terms and their definitions. Like, what is analysis? It is the process to provide chemical or physical information about a sample. Then what is sample? Sample is the material which is being analyzed. And then what is analyte? It is the component of interest in the sample which is being measured. So now you may be hearing some term like measurand. So what is a measurand? It is the quantifiable property of the analyte that is being measured. For example, the concentration of sodium in urine is a measurand. So I'll take one example and then it will be more clear to you. And then what is matrix? The remainder of the sample excluding the analyte is the matrix. Then contaminants, a substance including the analyte itself that is introduced unintentionally. Means you don't want to introduce it, but during the procedure, somehow it got introduced into your sample, like during collection or processing or measurement, then it is a contaminant. So let us see one example, determination of arsenic in water. So this is one analytical problem given to you. Say you have to determine arsenic in water. So in this, the analysis is arsenic in water, sample is water, analyte is arsenic, measurand is concentration of arsenic. And what is the matrix? All other things present in the water except arsenic, that is the analyte, are called matrix. Then what is a standard? You may be hearing very often standard addition, and many such things. So what is a standard? A substance or material with a known composition, concentration, and purity used as a reference to ensure the accuracy and reliability of analytical measurements. So that is a standard. And what is a primary standard? You may be knowing or aware of that there are primary standards and secondary standards. So a primary standard is a substance that is extremely pure, stable, has no water of hydration, and has a stable stoichiometry, and with a known formula weight. For example, sodium chloride, which normally is used to prepare standard for measurement of chloride. Now, what is a secondary standard? It is prepared by calibrating against a primary standard. For example, sodium hydroxide. When sodium chloride is a primary standard, sodium hydroxide is a secondary standard because it is hygroscopic, and when you keep it in open air, it absorbs water. So its stoichiometry is not fixed. Now, internal standard. What is an internal standard? It is added to sample to correct the variations during analysis. A known concentration of internal standard will be added to all your samples and blanks during the analysis, and that is called as an internal standard. And it is very much used in ICP MS measurements or ICP OS measurements that we will be coming in the future lectures. And what is calibration standards? These are solutions of known concentration used to create calibration curves, which are being used to find out the concentration of analyte in a sample when you are using an instrumental technique. So instrumental techniques are comparative techniques where you first need to create a calibration curve by using known standards, and then from that calibration curve, the unknown concentration can be found out. Now, spike. So, when a known concentration of a standard is added to your sample, so that is spike. So, this is a spike whenever we are adding an internal standard or standard are added, a standard addition. That is what standards are added to a sample or blank. So that is called a spike or spiking your sample. Now, standard addition. Addition of a known amount of analyte or spike to the sample to provide an internal calibration to the measurement. हम ये कर सकते हैं.
said.
So continuing our key terms and definitions, let us see now the technique, method, procedure, and protocol. These terms are very often comes while reading something or some books or some analytical chemistry book. When you are reading, very often we encounter these terms and we are normally getting confused. What is a technique? What is a method? What is procedure? And what is a protocol? To make it clear, now let us see what are those. So technique is any chemical or physical principle we can use to study and analyze. So let me show you one diagram, then it will be clear. See this diagram. So a technique, say graphite furnace atomic absorption spectroscopy. So this is an instrument and that is a technique. By that instrument or by that technique, you can analyze, say, lead. So lead in soil, you can analyze lead in water, or you can analyze lead in blood. So now these are different methods. Technique is GFAS, the graphite furnace atomic absorption spectroscopy. And methods are three different methods have been given here: lead in soil, lead in water, lead in blood. Again, each method can be like various analyte can follow different procedures for this method. Like lead in water, somebody may follow APHA method or somebody may follow ASTM method. Now, what is APHA? APHA is the American Public Health Association. They have some documented procedures for lead in water. So many analyte can follow that. Or somebody, that is American Society for Testing of Material, is the ASTM. So many can follow this method, this procedure. So in the method lead in water, procedures can be many. And what is a protocol? Protocol when you like some regulatory body is involved, like EPA. What is EPA? Is the Environmental Protection Agency. When you are analyzing some toxic metal like lead in water for some environmental regulatory, that time EPA will be involved and then your procedure becomes protocol. So now let us see the definition line by line. A technique is any chemical or physical principle we can use to study and analyze. Method is application of a technique for a specific analyte in a specific matrix. Now, set of procedure is a set of written direction telling us how to apply a method to a particular sample. Then what is a protocol? As I said you, the set of stringent guidelines specifying a procedure that must be followed if an agency is to accept the result. Like the case lead in water, EPA has to accept the results. So therefore it is a protocol. And as we have seen, a method may have several procedures as each analyst adopts it to a specific need. And protocols are common when the results of an analysis supports or defines public policy. For example, when determining the concentration of lead in water under the Safe Drinking Water Act, for example, labs must use a protocol specified by the agency, Environmental Protection Agency. So that time it becomes a protocol. So this is clear. Now the continuing the key terms and definition, we have already used the terminology qualitative analysis and quantitative analysis. So what is a qualitative analysis? It is the measurement to determine the identity, structure or physical property of a substance. And quantitative analysis is the measurement to determine the amount of concentration of an analyte in a sample. And what is a signal? It is the measurable response generated by an instrument or detector in proportion to the amount or concentration of an analyte. That means the concentration of the analyte is proportional to the signal produced by your instrument. So that is the signal. For example, in case of UV visible spectrophotometer, absorbance is the signal. In case of a emission spectrometer, emission is the signal. So now what is a detector? A detector is a device that responds to the presence of analyte, usually generating an electrical output. Say in case of UV visible spectrophotometer, when the light is passing through your sample, it is getting absorbed. And now what your detector is measuring actually is the initial intensity I0 and after absorption, the reduced intensity IT. But actually the light intensities are not measurable quantities by instruments. What instrument can measure is either a voltage or an electrical output. And therefore, in case of this type of instruments, the light is being changed into or converted into an electrical output, either current or voltage, so that the detector can measure it or the instrument can measure it. So now what is a total analysis technique? So a technique responding to the absolute amount of analyte is called total analysis technique. Mass and volume are the most common signals for this, and the corresponding technique, you may be knowing it very well, are gravimetry for mass and titrimetry for volume. So this is the total analysis technique. What is concentration analysis technique? A technique in which the signal is proportional to the concentration of the analyte. Since most concentration techniques rely on measuring an optical or electrical signal, they are also known as instrumental techniques. So these gravimetry and titrimetry, they are known as classical techniques, whereas whenever you are measuring a concentration, they are known as instrumental techniques. Now with this, now we will see the various basic overview of analytical concepts, how an analytical chemistry goes actually. So whenever an analyst or an analytical chemist is given with an analytical problem, so how to choose a method or how to choose an instrument which you are going to use for the analytical problem given to you. So for this, choosing a method, you have to consider these points. So you have to consider all these points one by one. First one is the scale of operation. This depends on the amount of sample available and the concentration range you are working. We will again see one by one each of these points. So first you just take an overview of what are the points we need to focus while choosing an instrument. The second one is sensitivity. Then means how the instrument, how it is separating from between two signals. Then specificity and selectivity, robustness and ruggedness, accuracy and precision, detection limit, linear dynamic range, analysis time, and finally, these 2 points are also important, like availability of equipment and cost. What is the running cost of your analytical method? So now let us see one by one elaborately. Scale of operation. What is it? So just focus on this picture. This is like the x-axis is mass of sample and the y-axis is concentration of analyte. So you can very well see the x-axis of mass of sample is macro, meso, micro, and ultra micro. It has been divided like that. So, and here the concentration is the major, minor, trace, and ultra trace. So you have to consider, for scale of operation, you have to consider the amount of sample available. For example, say you are dealing with some forensic sample which may be available in very less quantity. With comparison to that, a soil sample you have collected from site can be available in kg of quantity. So accordingly, you have to choose the analytical method. Then expected concentration of analyte, whether it is in percentage level, it is in microgram level, or it is in milligram level. Then the minimum amount of analyte that produce a measurable signal. That means the detection limit of your instrument. So collectively, all these, when you consider the mass of sample and the concentration of analyte, it is known as scale of operation of an analytical method. In this case, I have given one example, say, so micro trace analysis. What is a micro trace analysis? That means your sample is available in microgram quantity between 0.1 milligram to 10 milligram. You can very well see this is the region. And then contains a concentration of analyte between this. So this is the trace concentration. So accordingly, you can decide the scale of operation of an analytical method. Now, what is sensitivity? Sensitivity of an instrument or a method is a measure of its ability to discriminate between small differences in analyte concentrations. So there are two factors which limit sensitivity. What are the two factors? The slope of the calibration curve, which is accepted by IUPAC, and the second one is the precision of the instrument. But mostly everywhere you will find the first one, the slope of the calibration curve. Now actually what is a slope? Slope is dy by dx. That means the variation in signal per unit variation of concentration. So that is the slope, which means sensitivity. Means how your signal is varying per unit concentration change in your analyte. So now let us compare the two cases, comparing the sensitivity of a spectrometer for gold and silver. So now you see first one, this one is the for gold and this one for silver. Now what are the slope? The slope here you can see very well that slope for gold is 50 unit and for silver it is the 5 unit. So now obviously for a unit change in concentration, the change in signal for gold is 50 unit, whereas the change in signal for silver is only 5 unit. So that means sensitivity of the instrument for gold is higher than that of the silver. So that is what sensitivity means. So now let us see the specificity and selectivity. So analytical method is specific if its signal depends only on the analyte. Signal depends only on the analyte, while selectivity is used when the method is able to respond to several different analytes in the sample. So the ability to identify an analyte in the presence of other substance in a sample is specificity, and you may be knowing the antibodies are highly specific for its epitope or region of a protein, and therefore the antibody will be specifically goes and react with that. When lot of other proteins or epitopes are available, but one antibody will be specific for a certain, for one epitope only. So that is highly specific. Whereas selectivity is you can imagine one gas sensor. That gas sensor may be, say, CO sensor, carbon monoxide sensor. It is not that it is only it will only respond to carbon monoxide. No, it is not like that. It will respond to all such type of similar molecules. So it is a selectively from many other gas molecules, it selects CO. But for acetylene also, it can ring. Okay, so that is the of gas sensor selectivity is its ability to differentiate or target gas from all other gases in a mixture. So that is selectivity. Means for all the gases, it will have some signal, but for CO, it will have more signal. It is like that. Now, robustness and ruggedness. So all these terms actually you must have heard here and there, but so to give you clarity, these are the things you can refer anytime to these slides. So what is, for a method to be useful, it must provide reliable result. You all may agree that for a method to be useful, it must provide reliable results. But however, methods are subject to a variety of chemical and physical interferences, which contributes uncertainty to the analysis. So a method relatively free of chemical interferences and applicable to many analytes in a wide variety of sample matrices is termed as a robust method. Then what is rugged? A rugged method is a method relatively insensitive to changes in experimental conditions. For example, temperature, acidity, reaction time is called a rugged method. So normally it is a difference like chemical interference to physical parameters. So now accuracy and precision. I know everybody must be aware of accuracy and precision, and many times you must have used these things also. But to refresh your memory, just what is accuracy? It is how closely the result of an experiment agrees to the true value or expected result. So we can express accuracy by either absolute error or relative error or bias. So these are the three terms you must be remembering: absolute error, relative error, and bias. Okay, so and what is mu? Mu is the population mean for the concentration of an analyte, and xt is the true concentration. So this is, say, your measurement. Now for an unknown sample, your question may be, how do you know the true value? But this type of accuracy, and accuracy is defined when, say, for a certified reference material, for which you know the true value. The certified value is known because each certified CRM or certified reference material comes with a certificate of analysis. So you know the true value. And if you are analyzing the sample with your method, and then you can find out your absolute error or relative error or bias. So that will give you an idea about the accuracy of the method you are following. So what is precision? It is a measure of variability between the individual results. So normally whenever we are analyzing a sample, we will be analyzing it several times, not a single time. It will be analyzed several times. And now we have to see how the result, like for each analysis, for the same sample, for the same parameter, how the obtained values varies. For example, see the case A, where, say, you are analyzing potassium in a sample. So you can see all the analyses are lying very closely. The span is very less. So this is highly precise. Whereas in case of B, the distribution of all the values are quite large. So it is, if you are comparing A and B, then A method is more precise than B. So this is what precision. What is precision? And precision can be expressed by either standard deviation, variance, or relative standard deviation. So these are the parameters looking at which you can tell how the method is precise or not. Now the other terms are detection limit and linear dynamic range. Many a times, normally, students confused with sensitivity and detection limit. So as I have already told you, the sensitivity is the slope of the calibration curve. And what is detection limit? It is the minimum concentration or mass of an analyte that can be detected at a known confidence level. So mathematically, it is represented as the signal of detection limit is signal of average of blank and then some standard K, and this is the standard deviation of blank. So whenever you are doing a method or you are utilizing a method for a given sample, you have to run blank various times following the same method. Say at least minimum 6 to 10 times you should take the blank. Then for all the signals of the blank, you have to take the average, which will give you the average of signal for blank. Then you have to calculate the standard deviation by using the formula given in prior slide. And then you have to multiply 3 with the standard deviation, add to this. And then now this is your signal for detection limit, from which the concentration can be calculated as this 3 times standard deviation of blank divided by slope. This will provide you the concentration which can be detected by your instrument. Again, detection limit and quantification limit are two different things. At detection limit, you cannot report a result if it is close to your detection limit. For quantification limit, the same thing, the K can be taken as 10. So K equal to 10 for quantification limit. Okay. Now what is linear dynamic range? So linear dynamic range, you can have a look into this plot here, which is a typical calibration curve of an instrument where x-axis is signal and x-axis is concentration and y-axis is signal. So now normally you must have observed that the calibration curve never goes straight line in a straight line indefinitely. There is a curvature. So now let us look into the various region of this calibration plot. So now if you have taken standards from here, these are the various concentration of the standards you have taken. Say 4 points you have used to draw this plot, or 5 points, which is another point is in the curvature. So now this is your LOD, limit of detection. So now this is beyond your standard is the LOQ, limit of quantification, and the linear portion from this to this is the linear dynamic range, and from where it is getting deviated from linearity. So this point, from where the linearity, it is deviating from linearity, is the limit of linearity. So these are the various terminologies associated with a calibration curve. So now let us look into the, normally whenever we are using an instrumental method, as I have told you, we find out the concentration. Now concentration of an analyte. The concentration can be in terms of molarity or formality or normality or molality, weight percent, volume percent, weight to volume percent, parts per million or ppm, and parts per billion or ppb. So these are the name of the concentrations And these are the units, how it comes, and these are the various symbols used for that. Most often we use normally molarity. Very common is molarity, weight percent, volume percent, and sometimes weight to volume percent also. And parts per million and ppb are very common in trace analysis or ultra trace analysis. So let us see what are those. Now let us see like formality. Let us see the difference between molarity and formality. Formality normally many people does not use, but just to give an idea what is it. So both molarity and formality expresses concentration as moles of solute per liter of solution. However, the slight difference is that molarity is the concentration of a particular chemical species, whereas formality, on the other hand, is a substance total concentration without regard to its specific chemical form. Let us take an example, then it will be more clear. So, when a compound is there, the molarity and formality will be same if when it dissolves, it is not dissociating into ions. For example, say solution of glucose. You all know when you solubilize glucose in water, glucose will not break into ions. It will be remain as a glucose molecule only. For in that case, the molarity and formality are same. However, say the case of calcium chloride. This is a salt. When it is dissolved in water, it will give, say if you are taking 0.1 moles of calcium chloride in 1 liter of water, say. No, the solution will contain 0.1 mole of calcium and 0.2 moles of chloride. Is that clear? So the molarity of calcium chloride therefore is 0 actually, if you see like that. Calcium chloride, there is no calcium chloride as such in the solution. What are there present there? The solution is 0.1 molar in calcium 2 plus and 0.2 molar in chloride minus. But as such calcium chloride is not present in the solution. And therefore, if somebody will ask you calcium chloride molarity is what, then it is not there, it is 0. But yes, 0.1 molar calcium is the calcium 2 plus is there and 0.2 molar chloride minus is there. However, the formality, when you take the formality, it is 0.1 formal because formality sees the compound total. So actually, when we tell like 0.1 molar calcium chloride solution, it is actually formality, not molarity. But normally in analytical chemistry, it is called as molarity. So rigorous definition of molarity is largely ignored in the current literature. Then percent, what is a percent? It is weight percent or volume percent or weight to volume percent expresses concentration as the unit of solute present in 100 units of solution. For example, a solution that contains 1.5% weight by volume of NaCl means it contains 1.5 gram of NaCl in 100 ml of solution. So that is what percent. Then what is a parts per million or parts per billion? These two terms, ppm and ppb, are very often used in analytical chemistry, trace analysis or analytical chemistry. So the ppm and ppb are ratios that gives the grams of solute in respectively 1 million or 1 billion grams of the sample. For example, a sample of steel contains 450 ppm in manganese. That means 450 microgram of manganese for every gram of steel. That is what it means. So, how if we approximate the density of a solution, aqueous solution as 1 gram per ml, then for aqueous solution, we can use the same terminology as ppm or ppb. Though actually, if you see, then it is used for weight to weight, like microgram per gram. But for aqueous solution, which normally is the case when we are doing trace analysis, we use the term ppn and ppb considering the density of water as 1. So therefore, ppm means microgram to gram, which can be equivalent to milligram to liter, and so on. So this is the definition. Now, what is stoichiometry? Because stoichiometry is very much important in case of your chemistry. So stoichiometry is the quantitative relationship between reactants and products in a chemical reaction. And what is its importance? Actually, it ensures balanced reaction, helps determining the reactant and product quantities, how much is required for the reaction to complete, and then it is crucial for chemical analysis and synthesis purpose for calculation and all. So the mole ratio is the relationship between moles of reactants and products. Law of conservation mass has to be kept, and the mass of reactants should be equal to the mass of products. And actually, it is required to determine the limiting reagent. And from that, you can calculate the how much, if this much of reactant you are taking, then how much a product can be formed from that. So that can be calculated if you know the stoichiometry. So say for example, a balanced reaction which defines the stoichiometric relationship between the moles of reactant and moles of product is known as a balanced reaction, which provides the basis for many analytical calculations. For example, consider the reaction here, an analysis of oxalic acid in which Fe3 plus oxidizes oxalic acid to CO2. So here you can see 2 moles of Fe3 plus are required to completely oxidize 1 mole of oxalic acid. So from this balanced reaction, we are able to say that 2 moles of Fe3 plus will be required for complete oxidation of 1 mole of oxalic acid. So that is what the balanced reaction shows us, that 1 mole of oxalic acid reacts with 2 moles of Fe3 plus. So we can use this balanced reaction to determine the amount of oxalic acid in a plant sample if you know the moles of Fe needed to react completely with the oxalic acid. So now the thing is, many times when we receive the sample, they are not in a form that can be directly analyzed by the instrument. Say when you are receiving aqueous samples or environmental water samples or any solution sample, you can directly take it to the instrument and analyze it by using some standards. But it is not the case always. Many a times we receive solid samples also, soil samples, plant samples, and many metal alloys and all. So for those type of things, you have to dissolve the sample. You have to bring it to a solution form so that an instrument can utilize that for analysis purpose. So how to now dissolve a sample? There are various methods you have to follow for its dissolution, and which method you will follow depends on the type of sample. So here I have listed the various dissolution techniques, and I have given one example for all. So say for normal water soluble, if something you receive some sample, say NaCl, sodium chloride sample, you have to analyze for some other elements, say potassium or something, or magnesium. So you need to analyze potassium or magnesium in sodium chloride sample. Then you have to just dissolve in water. So aqueous dissolution, in this, dissolve the sample in water or buffer solutions. So where it is applicable to soluble salts, sugars or acids. Example is dissolving NaCl in water. Acid dissolution, which uses acids like hydrochloric acid, nitric acid, HF or perchloric acid to dissolve metal oxides, alloys, minerals, or biological materials. And applications are towards metals, inorganic compounds, biological matrices, and for example, one example is dissolving steel in aquaregia. So like this fusion technique, so there are various fusion materials actually with a flux which are known as flux. So you have to heat your sample in a flux, say sodium carbonate or lithium tetraborate or lithium metaborate, like that, and then they are converted into a solution form. So you have to use this fusion technique when refractory materials like ceramics are there, aluminum oxide or some titanium boride or zirconium boride. So these things you have to follow a fusion technique for dissolution. So like example is dissolving alumina with sodium hydroxide fusion. Alkali dissolution, so uses bases like NaOH, KOH to dissolve organic or inorganic samples. So applications is silicates and polymers. Example is dissolving silica with molten NaOH. Then microwave assisted dissolution, this is the best one actually. If you can have a microwave dissolution technique, then you can use this like microwaves for rapid heating and with acid analysis. And it is not like that microwave, like house microwave. The microwave system for sample dissolution, it is somewhat different. And in many labs, you can find them. Applications are all type of samples. They have their own methods written there how to dissolve the sample. So application are towards organic matrix, metals, soils, etc. Then dissolving biological samples for trace analysis. So there are use enzymes for dissolution of biological sample. Mostly for biological samples, this will be used. Applications are to proteins. You know, proteases are there, which can break the protein and bring them to solution form, and then tissues or dissolving protein using proteases. So now high pressure digestion. Microwave is also one type of high pressure digestion where you actually use a different type of vessels which can withstand high pressure around 100 to 200 bar, and then you add acids and then you subject it to microwave heating, then high pressure will be built up, will facilitate the dissolution. For example, rock, mineral, glass, and zirconium silicate with HF in Teflon line vessels is one of the example. So now you have to utilize any one of these dissolution technique, and dissolution method you will finalize after looking at your analytical problem. What you want to dissolve and which instrument you are going to use. And based on that, you have to choose a dissolution technique. Now, once you have dissolved dissolve your sample, now it is prepared to be taken for your instrument. But then all the instruments are comparative techniques. So you have to prepare a standard solution. So how to prepare a standard solution? So in standard solution, the terminologies are that what is a standard solution? It is a solution whose concentration is known to a high degree of accuracy. So in that, normally there will be a high concentrated solution from which you have to dilute it, and then you need to prepare the standards which will be used as calibration standard. So now what is a stock solution? A stock solution is prepared from its a standard like primary standard, or you can prepare from a stock solution you can purchase from well-known companies like Merck and many other companies are there who sell standard solutions. So from there you can procure it. So now a stock solution is prepared by weighing out an appropriate portion of a pure solid or measuring out an appropriate volume of a pure liquid, placing it in a suitable flask and then diluting to a known volume. So you have to use this type of volumetric flasks. You have to use this type of calibrated pipette. You may use a glass pipette to take your volume, and then you have to make up the volume. And then you need to calculate the concentration. So now the calibration standard solutions. Calibration standard solutions are often prepared by diluting a more concentrated stock solution. Then our known volume of the stock solution is transferred to a volumetric flask and deionized water was added to make up the volume. So now what is deionized water? These are actually analytical grade water. You cannot use in your analysis, you cannot use the normal water or tap water because it may contain the analyte to a higher concentration so that your values will be wrong. So you need a water for all dilutions throughout your analytical purpose which does not contain the analyte. So for that you need to a analytical water purifier. Say Merck Millipore water purifier is available and Sartorius water purifier is available. So many companies are there who provide you to produce analytical grade water, and that is called as deionized water. Means all the ions were removed from the water and it is made for analytical purpose. So make up the volume. Now you can use the N1 V1 equal to N2 V2 or the concentration into volume to the diluted concentration and volume for calculating your concentration of your final standard, whatever you are preparing. And for that, how much volume of the stock solution you need to take. So C0 is the stock solution's concentration, B0 is the volume of stock solution needed, CD is the concentration of the standard solution, and VD is the volume of the standard solution. So you know the concentration of stock solution, you know how much concentration of the standard to be prepared, and then you will be having a volumetric flask of known volume. Then you can calculate the how much volume of the stock solution you need to take for preparing say 50 ml of this concentration. So that is why how you can calculate it. So now let us see what is a gravimetric analysis. So with all this, now in this lecture we'll cover the classical analytical technique, that is gravimetric analysis and volumetric analysis. We will see, and from next lecture onward it will be the instrumental techniques. So what is a gravimetric analysis? It is a quantitative classical analytical method. It is a quantitative method and it uses mass as an analytical signal. So it is total analysis. As you may be remembering, in the initial stages we have seen what is a total analysis and what is a concentration analysis. So it is a type of total analysis which uses mass as an analytical signal, and it is based on the formation of a pure, stable and weighable product, so that you can weigh it and find out what is the amount of the analyte present in your sample. So what is the principle? It relies on the conservation of mass, and accurate gravimetric analysis requires that the analytical signal, whether it is a mass or a change in mass, if you are doing thermogravimetry, is proportional to the amount of analyte in your sample. And it involves precipitation, filtration, drying and weighing, requires accurate and selective precipitation of the analyte. So what are the various types of gravimetry? It's the precipitation gravimetry, and one small example is given everywhere. When the signal is the mass of a precipitate, for example, determination of chloride by precipitating silver chloride. You all know silver chloride gets precipitated. Like if it is a silver nitrate sample and you need to see how much silver is present there, then you can add HCl so that the silver chloride will be precipitated, and then you can filter it and weigh it. So it is the precipitation gravimetry. Then electrogravimetry, it is the deposit the analyte as a solid film on an electrode in an electrochemical cell then where it is like the reduction of copper 2 plus to copper at a platinum cathode. So that is one of the example. So volatilization gravimetry, thermal and chemical energy is used to remove a volatile species or moisture content of a bread. If you want to see what is the moisture content of a bread, then you can do this. Then particulate gravimetry, separating the analyte from the sample matrix using a filtration or an extraction. So determination of total suspended solids in wastewater. So these are small definition with one example each of various types of gravimetry. So there are total 4 types of gravimetry, and everywhere it is related to measurement of mass. You have to determine the mass from where you are going to calculate the analyte. Now for precipitation gravimetry, an insoluble compound forms when we add a precipitating reagent or precipitant to a solution that contains our analyte. So now what are the important points you have to focus when you are using this method? The precipitate must be of low solubility, of high purity, and of known composition, as its mass has to reflect accurately the analyte's mass. The precipitation must be free from impurities, otherwise the impurity also will contribute to the mass, leading you to a wrong estimation of the analyte. Proper filtration of the precipitate, it should not get lost when you are filtering it. Rinsing the precipitate, where to rinse? To remove the residual traces of supernatant without incurring loss of analyte due to solubility. Then drying the precipitate, obviously you have to dry it, because otherwise the moisture or the water content or the solvent also will contribute to the weight, leading to a wrong result. So you have to dry it completely. So dry the precipitate to remove the residual traces of rinse solution and to remove any volatile impurities if present. Then the composition of the precipitate. For a quantitative application, the final precipitate must have a well-defined composition or stoichiometry. So that you have to assure. So you can see the various precipitation method. It is shown like this. You need to use a glass rod while pouring the solution to the funnel. It will ensure there will be no loss of your solution. Or you sometimes, if they are very fine precipitates, they tend to clog the filter paper and it will not go fast. In that case, you can use a vacuum filtration setup. So let us take the example for this method, precipitation gravimetry, determination of magnesium in water and wastewater. Here magnesium is precipitated as this magnesium ammonium phosphate, using this as the precipitant. This ammonium phosphate is the precipitate. So the precipitate solubility in the presence of dilute ammonia is very low. So that ensures the low solubility. And because of this precipitate is not selective, a preliminary separation of magnesium from potential interference is necessary. Otherwise, other interfering element may get precipitated with magnesium, and then you will be wrongly estimating the amount of magnesium. So beforehand, if you are following this method, then you have to separate the various interference. So calcium is one of the interferent. So you have to separate calcium by precipitating it as its oxalate. So now the precipitate is isolated by gravity filtration using a rinse solution of dilute ammonia, because in dilute ammonia its solubility is very low. So you have to use dilute ammonia for rinsing the precipitate, otherwise the precipitate may tend to get solubilized and lost. Now after filtering, the precipitate is converted to magnesium pyrophosphate and then weighed, which is a stoichiometry of stable stoichiometry and weight. But the drawbacks are co-precipitation can happen, incomplete precipitation can happen, losses during washing or drying. This requires a knowledge of conditions for proper precipitation, drying and measurement. So skill skill is very much important here. You have to develop the skill. Then applicable to larger sample size, because whatever precipitate you are generating should be of weighable quantity. Otherwise, error will be there. If you are using very less quantity, very milligram, few milligram, then there will be weighing error. Time taken for analysis is long. Procedure is rather tedious and applicable only to a limited number of analytes. So now let us see the volumetric methods of analysis. So that is what gravimetry, and as I have told, the precipitation gravimetry is the most widely used method. So I have only covered that one. So now volumetric method of analysis, let us see. It is a quantitative classical analytical method. Again, it is a classical analytical method. Like that, gravimetry also was a classical analytical method, and determines the concentration of a substance by measuring the volume of a solution required for a reaction. In case of gravimetry, it is the mass, here is the volume. It is also known as titrimetric analysis. Now, what is the principle? It is based on a chemical reaction between the analyte and a standard solution known as the titrant. So the reaction must be stoichiometric or fixed mole ratio, rapid, it should occur quickly, and there should be a detectable endpoint marked by an indicator or an instrumental method of measurement, so that you can easily detect the endpoint, which will ensure you are not going to add any extra volume of your titrant. Now, what are the various terms used in volumetric analysis? A titrant, that is the standard solution of known concentration, is known as titrant. Analyte, again, the solution being analyzed is the analyte, and then equivalence point. There are 2 points. One is equivalence point and one is end point. This you have to mark it. So equivalence point, equivalence point is that point where the reactants are in stoichiometric proportions. That is the equivalence point. But it so happens that exactly at the equivalence point, you cannot identify that the reaction is being completed. And the end point is the point where it is observable change in signal we can look. So this is the end point, and difference between end point and equivalence point, where you are getting an observable change in signaling, that is the end point. Okay. So what are the various steps in volumetric analysis? It is common to all volumetric analysis. So it is the prepare the analyte and standard solution, titrate, add the titrant to analyte until the endpoint is reached. Observation is detect the endpoint using an indicator or instrument. Now, instrument means potential measurement or pH measurement. So these are the instrumental methods when you are not having an indicator. An indicator means you will look into the change in color. So that is the observation. Now you have to calculate, use the titration data to determine the analyte concentration. So there are again 4 types of volumetric methods. You all may be knowing this. They are acid-base titration, complexation titration, redox titration, and precipitation titration. Let us see one by one. So what is a acid-base titration? You must be aware of this. So acid-base titration is a quantitative analytical method used to determine the concentration of an acid or base in a solution by reacting it with a base or acid of known concentration using an indicator to detect the equivalence point. In the absence of an indicator, either a pH electrode can be used or a potentiometer also can be used, resulting in a potentiometric titration curve. So let us take the example. Say this is one example. You yourself also can do. 25 cc of 0.5 moles per liter HCl was neutralized by 38 cc of calcium hydroxide. So the calcium hydroxide, this much calcium hydroxide is needed for neutralizing that. So what was the concentration of the alkali? So now you have to calculate the concentration of the calcium hydroxide. To do this, you must know the balance equation between this calcium hydroxide and hydrochloric acid. So you have to your first step is to write the balance equation. So in this case, it is calcium hydroxide and then it is HCl. And what will form this calcium chloride? Water. Because any acid-base titration, finally, it will result acid plus base, salt plus water. So this is the salt and this is the water. So now you see 1 mole of calcium hydroxide is required to neutralize 2 moles of HCl. So this is what is very important, this mole ratio. So now step 2, calculate the number of moles of HCl. So 25 cc of 0.5 moles per liter hydrochloric acid. that means total mole is this much. And now what is step 3? Calculate the number of moles of calcium hydroxide using mole ratio. See, as you have seen in the balance reaction, 1 mole calcium chloride requires 2 mole of HCl. So now you have to use 1:2, 1 mole, 2 mole. So now we have to calculate this one. And this we have already calculated here. You can see here. So now if this is the molarity number of moles of HCl, then it will record this by 2 because the mole ratio is 1:2. So you can calculate accordingly. This is the moles of calcium hydroxide. So now what is a complexation titration? So the complexation titrations are quantitative analytical methods where a solution containing metal ions react with a ligand to form a stable soluble complex with the end point detected using an appropriate indicator. Now, what are the key features that based on a metal ligand complex formation? Common selecting ligand normally used is EDTA because most of the time EDTA is a hexadentate ligand and it forms 1:1 complex. So therefore it is the mostly used reagent and used to determine metal ion concentration. Let us take the example of determination of calcium in water. So what are the various steps? Stepwise we will go. So sample preparation, take a water sample containing calcium ion. Buffer addition. Now this condition is so that you have to maintain a pH 10. So you have to use a ammonium buffer to maintain the required alkaline condition for complex formation. So formation of complex of calcium with EDTA will highly efficiency is very high at pH 10. So all this you can get from any standard analytical chemistry book. So whenever you are going to use this type of titration, you have to first look into the chemistry. What are the conditions where the complex is forming and all, and accordingly you have to prepare your sample. So now in this case, you have to add an ammonium buffer to maintain the pH 10. Then here in this case, the indicator is aerochrome black tea indicator, where the solution turns wine red in presence of calcium. So now see, this is the calcium is there, aerochrome black tea, that indicator is added and it is here. Now, when the end point reaches, then you titrate this with standard solution of EDTA. When the end point reaches, so purple at the titration's end point, it will change into purple color and it will be changing into blue totally at the blue after the end point due to the presence of on-complex indicator. So you have to see, this is a markable change from wine red to purple. So now you have to mark this change and then you have to stop at that point. If you are adding any extra amount of indicator, then it will lead to a wrong result during calculation. And you can see this. So far I have given here these three various colors, how it is changing. Then you have to titrate. Titrate the sample is standard EDTA solution. EDTA chelates calcium ion forming a stable calcium EDTA complex. Endpoint, at the endpoint, all calcium are complex. Indicator color changes from wine red to blue. So you have to calculate, and the calculation is again N1V1 equal to N2V2 or mole M1V1 equal to M2V2. You know this calculation formula right from BSc level. So this is the calculation thing you have to do. Now let us see the redox titration. So what is a redox titration? The name itself tells that here it is a reduction, oxidation, both are happening. So our titration method based on an oxidation reduction reaction between the analyte and titrant is a redox titration. The various key features for this are, this involves electron transfer between species. As you must be knowing what is a oxidation. Oxidation is a removal of electron, or so electron will be transferring from one species to another species. So from where electron is to be drawn, that will oxidize, and who is accepting, it will get reduced. So it requires a redox indicator or a potentiometric detection of the endpoint. So either you use a potentiometer to see the endpoint, or a redox indicator you take to see the endpoint. The example is determination of iron 2+ in a solution. So now the determination of iron 2+ in a solution by redox titration. Step 1, again preparation of reagent. Now here you require standard solution of KMnO4. So prepare a standardized solution of KNO4 in distilled water. And KMnO4, you know, acts as a strong oxidizing agent in acidic medium. So now, therefore, you have to use acidic medium, use dilute sulfuric acid to acidify the Fe2 solution. The acidic conditions are necessary to ensure MnO4- reduced to Mn2+ instead of forming MnO2, which will give a black precipitate. So you have to acidify that. Now, what is the step 2? Is the, see, now you need to know the balanced chemical reaction is very important in this case also. So this is the chemical reaction. In this redox reaction, Fe2+ of ferrous ion is oxidized to Fe3+, and MnO4- of that permanganate ion is reduced to Mn2+. What is the indicator? KMnO4 itself is a self-indicator here, and the solution changes from colorless to light pink at the end point due to excess MnO4-. Now, how it goes, like you have to pipette a known volume, say 25 ml of Fe2 solution into a clean conical flask. Add few ml of H2SO4 to acidify it. Now fill the burette with KMnO4 solution. Ensure no air bubbles are present in the burette tip. Now you have to titrate it. Slowly add KMnO4 from the burette to the Fe2 solution while swirling the conical flask. Observe the disappearance of purple color of KMnO4. Like once the KMnO4 is falling into the flask, immediately where it is falling, you look the purple color. But once you swirl it, then the purple color will vanish because it will be utilized in oxidizing Fe2+ to Fe3+. So, but at the end point, when all the Fe2+ are consumed, then the pink color will retain. So the end point is reached when the light pink color persists for 30 seconds, indicating a slight excess of MnO4-. So that is the end point. So you have to calculate now the volume of KNO4 used, to record the burette reading to determine the volume of KMnO4 solution used. And you know this is the reaction. So you know that the mole ratio of Fe2+ to MnO4 is 5:1. You can see there 5, and here it is 1. So concentration of Fe2+ can be calculated using this formula. So this is what it is very important, that you should know the stoichiometric equation, the balanced equation. So that is very much important for this. Now, why acidic medium is required? Because as I have told you, it is to prevent the formation of MnO2, which is a brown precipitate, and ensures complete reduction of MnO4- to Mn2+ only. Because when something is getting oxidized, like your Fe2+ is getting oxidized to Fe3+, at the same time your here Mn is getting reduced to Mn2+. what is the oxidation state here? Mn, it is +4, +7. So from there it is going to +2. So that you have to avoid formation of this. Otherwise, you will end up with a wrong result. Now, where KMnO4 is titrant? Because KMnO4 is a strong oxidizing agent and provides a clear visual endpoint without requiring an external indicator, and therefore KMnO4 is very suitable for this type of reduct titrations. So now you have to when you are doing such type of titrations, you have to take care of a few things. Now the solution is properly mixed by swirling during titration, so that you are physically mixing, or you are bringing the Fe ion to in the vicinity to the permanganate solution, and use freshly prepared KMnO4 as it can decompose over time. So this method is widely used in environmental and industrial analysis to determine iron concentration in various samples. So now let us look into the precipitation titration, again a titration method where the analyte reacts with the titrant to form an insoluble precipitate, that is precipitation titration. So indicators are required, specific indicators, for example chromate ions are used to detect the endpoint. Example, Mohr's method, chromate forms a red precipitate of Ag2CrO4 at the endpoint. Now, endpoint detection, how to detect the endpoint? Endpoint is determined by the appearance or disappearance of the precipitate or a color change depending on reaction to reaction. And reaction requirement that reaction should be very fast and stoichiometric. Again, stoichiometry is very important here also. So let us look into one example. So determination of chloride. So add a known volume of chloride solution into a flask, add few drops of potassium chromate indicator, titrate with silver nitrate until a red precipitate forms. In Mohr's method, silver nitrate reacts with chloride ion to form silver chloride of white precipitate. So this precipitate will form. The chromate indicator produces a red precipitate or silver chromate after chloride precipitate is over. So now once you look into a red precipitate, that is your endpoint. You have to end there. So using the volume of AgNO3, you can calculate the concentration of Cl-. So see, this is the initial, it will look like this. Then AgCl is forming white precipitate. Once chloride is finished, then you will get a pink or reddish type precipitate. So that is your endpoint. You have to stop your reaction, and that is the volume of titrant you have to use. Now let us see what is potentiometry. This is the last topic for today's lecture. It is a potentiometry. What is that? It is a technique used to measure the electrical potential or voltage of a solution to determine the concentration of an analyte. What is the principle behind this? The potential difference between a reference electrode and an indicator electrode is measured, which is proportional to the analyte concentration according to the Nernst equation. You all must be knowing the Nernst equation. Otherwise also we'll be looking more into this when we are covering electrochemistry. So that time, so this is the Nernst equation. So it is applied, like what are the various applications? The determination of pH is one of the widely used of potentiometry. So that is using a glass electrode. We very now and then we use pH electrode for measuring pH, and that is nothing but potentiometry. The measurement of ions like sodium, potassium, chloride and fluoride ions by ion selective electrodes. So this is where potentiometry works as, and this is a typical setup or typical apparatus for your potentiometry. This is the reference electrode or saturated calomel electrode, and now this is where you are going to add your titrant, and then this is the working electrode. So reference electrode, indicator electrode, salt bridge and voltmeter to measure the potential difference are the components. And what is the working principle? A titrant is added gradually and the potential is monitored. The equivalence point is determined from the sharp change in potential. When the end point will reach, you will look into a sharp change of potential. The measured potential is related to the activity, or that is concentration of the ions in the solution via Nernst equation. This is the potential is equal to standard potential plus RT by NF into analyte. where E is the measured potential, E0 is the standard potential, N is the number of electron transport, R is the gas constant, T is the temperature, and F is the Faraday constant. So, this lecture has been prepared, and these are the from referring to various standard books. Here I am giving two books, Analytical Chemistry by David Harvey. This is online available. You can download the full book also, and it is a very good book. And another one is Spook, Holler, and Crouch, Instrumental Method of Analysis by Spook, Holler, and Crouch. So with this, and then one quote for analytical chemistry: the elegance of analytical chemistry lies in its ability to make the invisible visible. With this, I end this lecture. Thank you. Okay. If any of you have any question or anything, you can mail to me. My mail ID is given in the first page itself, and also my phone number is given. You can have right now. They can ask some one or two questions. Also, you can ask because 10 minutes, 5 to 6 minutes are there. If anyone need to ask or want to ask anything, you can ask. If there is no question anyway, you first go through the slides and then you can mail to me anytime. And I think it is my mail ID is clearly written in the first page. Even in the next class, you can go through this class, and then in my next class, you can ask me any question based on this class. Okay. Again, thank you.